Hello, and here we are to do the optics review for regular physics, and we've got some sketches of the ray diagrams. First one goes in parallel, reflected down through the focus, and then through the focus, reflected out parallel. And where those two rays cross will be our image. And if I was to describe this image, it is on the same side as the object. It is inverted. It is a larger image, and it would be a real image. For the second one, you're in front of the focal point with a concave mirror. You still go in parallel, reflected down through the focal point. But since you're in front of the focal point, you have to go up from the focal point, and it's reflected out parallel. Those two rays will never meet up, so you have to trace back. And where they appear to meet would be your image. And this image would be on the opposite side. It is erect. It is larger. And this would be a virtual image, because the rays don't actually cross. You have to trace back to find them. Then convex mirror, if you went in parallel, it's reflected from the focal point. And for a convex mirror, it's a diverging mirror, so you want to make sure you're always using the focal point on the opposite side. So when we go in towards the focal point on the left while drawing on the right, it's reflected out parallel. Those two rays will never meet up, so we have to trace back and see where they appear to cross, and that would be our image. This image would be on the opposite side. It is erect. It is smaller, and this would be virtual, because those light rays didn't actually cross. Then we go to lenses. For a convex lens, start in parallel, then the light is refracted through the focal point. Then you go through the focal point, and it's refracted out parallel. And where they cross, that's where your image would be. And this image's location would be on the opposite side. It is inverted, minus smaller, and this would be a real image because those light rays actually cross there. For the next one, we're inside the focal point, so you go in parallel, refracted through the focal point. And when you're in front of the focal point, you have to line it up as if it's coming from the focal point. I'm going to extend my lens a little bit, and then it would be refracted out parallel. Those two rays would never meet up, so we're going to trace back, see where they appear to meet, and this would be our image. That image would be on the same side as the object. It is erect. It is larger. This would be virtual. And the last ray diagram is for a concave lens. And this one doesn't matter if you're inside the focal point or not, because you're always using the focal point on the opposite side. So if I go in parallel, I'm going to diverge or spread out from that focal point, away from the focal point. If I'm going in on the left, I go towards the focal point on the right, and then it's refracted out parallel. Those two rays will never meet up, so we need to trace back, find where our image will be. And our image is on the same side. It is erect. It is smaller, and this would be virtual. So in summary, you should notice that converging lenses and mirrors can produce which kinds of images? They can produce upright and virtual and larger when you're inside the focal point. And then when you're outside the focal point, it can be inverted and real, and it can be larger or smaller. So converging lenses and mirrors can produce all of those. Diverging lenses and mirrors can only produce upright, virtual, smaller images. No matter what you do, that's all you can get from them. And going to the mathematical problems. In the back, number 1, Sally uses a giant concave mirror to burn a piece of paper and help find her focal point. She finds it burns best when it is 0.78 meters away from the mirror, so that's my focal point. If she then uses the giant mirror to pluck her eyebrows, holding it a distance of 0.3 meters from herself, so that's the object distance, where would the image of her eyebrow be located? So I'm going to use 1 over f equals 1 over dou plus 1 over die. So 1 over 0.78 equals 1 over 0.3 plus 1 over die. For that, you should get an image distance of negative 0.49 meters. Remember, what the negative means is that this will be a virtual image. Then it asks, how large would your 0.04 meter eyebrow appear? So we're going to do high is to ho as negative die is to do. So high is to 0.04 meters as negative 0.49, so that's going to make it a positive, is to 0.065 meters. Sorry, is to 0.3 meters. My bad. From that, you get the image height to be a positive 0.065 meters. Since this is a positive number, that means it's an erect image. And then number 2, a converging lens with a focal point of 18 centimeters or 0.18 meters is used to view a small 4 centimeter tall bug. What kind of lens is being used to view this bug? If it's a converging lens with a positive focal point, this is a convex lens. To find the image distance, I'd use 1 over f equals 1 over dou plus 1 over die. So 1 over 0.18 equals 1 over 0.085 plus 1 over die. And I'd get an image distance of negative 0.16 meters or 16.1 centimeters. And this negative means this is virtual. What's the image height? If we did high is to ho, which if it was 4 centimeters tall, that'd be 0.04 meters, as negative die is to dou. We get an image height to be 0.0758 meters. And the fact that this is a positive number means that this is erect. Okay, next one. Determine the focal length of a concave lens which produces an image with a DI of 12.9 when the object is 32.4 centimeters. So we're looking for f. So 1 over f equals 1 over negative 12.9. I'll trace centimeters on this one, and 1 over 32.4 centimeters. When you then solve that for f, you get negative 21.4 centimeters. And for the last one, a convex mirror is used in a parking garage. The focal point is negative 3.5 meters, and a car is 8 meters. What's the magnification ratio? So I first need to find DI. So 1 over negative 3.5, that's our focal length, is 1 over 8 plus 1 over di. One divided by negative 3.5 minus 1 divided by 8. Then you always have to make sure you take the inverse of the answer. So I get di is negative 2.43 meters. And so the magnification ratio would be negative di over dou. Or negative 2.43 divided by 8. And I get 0.3 for the magnification.